Hello, everybody. This is Dr. Jeff Thomas, and this is the lecture on waves, which aligns with Chapter 10. So, before we get started, I want you to look at the image on the right. What patterns do you notice about it? Well, if you said that there was a repeating pattern of ocean waves, that's very similar to what I was thinking that you might say. So, what we're trying to do here is define what a wave really is. And a wave is a repeating motion that transfers energy through matter or through space, such as light or sound, or mechanical waves as well, which includes ocean waves. Now, just to kind of give you an idea, waves transmit energy and not matter, which is an oftentimes a misconception that waves transfer matter. It doesn't. And let's take this for example. Light, which can travel through space, which does not have any matter associated with, does not need a medium in order for it to travel. Think about it. The light from the sun gets to Earth and it does not have a medium to travel through it. So it's only transmitting energy, not matter. So what we're going to be talking about in terms of waves, we're going to break this up into two major categories. The first one, we're going to discuss wave characteristics. The second one is going to be wave behavior. So let's talk about wave characteristics first. First of all, there are two major types of waves. We have transverse waves, which move up and down perpendicular to the motion, and this includes things like ocean waves or seismic waves. Other waves are called compressional waves, and these waves move back and forth in the same direction as the wave travels. So if we look at these two particular images right here, so you can see that this person's hand right here is moving up and down. So this energy of moving up and down, this oscillation up and down, that energy is being transmitted through what looks like a slinky, and it goes in an up and down motion. However, you can oscillate things as well going back and forth, just like what this hand is actually kind of depicting with the arrows. So if you take a slinky and you go back and forth, what you're going to get is you're going to get these areas of expansion right here, and then these areas of compression. And this kind of wave right here is called a compressional wave. However, sometimes they are called longitudinal waves as well. So let's look at an example of compressional and transverse waves. So this image right here that we're looking at, or I should say this simulation, these are a simulation of seismic waves. So seismic waves are earthquake waves. And when an earthquake occurs, it produces three different kinds of waves. What's known as a P wave, an S wave, and then surface waves. So what we're looking at right here is, in terms of looking at these three different types of waves, let's look at a P wave first, which is the very, very, very top. Do you think this is depicting A, a transverse wave, or B, a compressional wave? If you said compressional wave, you're correct. And we have a couple pieces of evidence from this simulation that kind of provide support for this claim. So first of all, if we look at this red dot right here, it is moving back and forth, back and forth, back and forth. It's not moving up and down, which would be more indicative of a transverse wave. In addition, right here, you might see this little yellow box right here. And you can see that it's compressing and then expanding, compressing and expanding. And that's actually an example of a characteristic of a compressional or longitudinal wave. Now, S in surface waves are more transverse waves, and you can clearly see this. For instance, if you look at the red dot in both cases, both an S and a surface wave, they are both moving up and down. And you can see in the S wave, in that green box, that it also is moving up and down. Another indication right here that we know that that waves do not transmit matter but rather energy is that you could see each one of these boxes basically represents a molecule of the Earth. And you can clearly see that the matter is not moving. It's not transmitting matter. Instead, it's transmitting the energy from one piece of matter, or what's in this particular case a box, to the next box. So again, waves only transmit energy, not matter. Okay, let's continue. So there are a couple important wave properties that we're going to go over that include amplitude, wavelength, and when we're talking about wavelength, we're going to talk about crest and trough, frequency, as well as speed. So now remember, before we move forward, any oscillating direction up and down is going to form a transverse wave. Any oscillating energy that goes back and forth, that's going to produce a longitudinal or compressional wave. Let's talk about amplitude. Amplitude is really how big the wave is. And amplitude is directly proportional to the amount of energy that a wave is transporting. So let's look at a transverse wave first, because that's a little bit easier to understand. Now imagine a hand with a slinky is moving up and down, and that's the oscillating motion. So before it begins moving, we have this line right here, this baseline, which represents 0, that there is no energy being transmitted by this particular wave. However, as you start oscillating up and down or back and forth, what you're going to do is you're going to create a wave. The top of that wave, which is known as a crest, and where we start off at 0, or that baseline, the difference between the two is called amplitude. So again, this right here, this line, as indicated right here, is the resting position, which is halfway between the crest and the trough. So this right here means no energy is being transmitted. So the further away from this line, this resting position you are, the greater the amount of energy that particular wave has. So that oscillating motion obviously has to be greater in order to transport that energy. Now for a longitudinal wave, that's a little bit different. Think about the slinky again. If you're taking a slinky and you're, instead of oscillating up and down, you kind of go back and forth. So what ends up happening is some parts of the slinky get very, very tight, like this right here where I'm pointing to. And that's called compression. However, you're also going to get parts of the wave that are very, very far apart, which is like right here, and that's called rarefaction. So what we're really referring to in terms of amplitude is when you have the closeness of the coils within the slinky are very, very, very close together. The closer they are together, the more energy that particular wave actually has. And that's the way we measure amplitude for longitudinal waves. So let's look at wavelength now. So I'm going to use the same image. So wavelength, there's a couple things we need to know first. We need to know the words crest and trough. So when we're looking at a transverse wave, a crest is the top of the wave, trough is the bottom of the wave. And the reason why that's important is because we use those locations to really identify the wavelength of a wave. So in this particular case, we can measure from crest to crest right here, where I'm pointing, and that would be the wavelength. Now, you can also measure it, as indicated right here, by trough to trough too, which is also wavelength. In fact, it really doesn't matter where you measure if you're going to measure the wavelength of a transverse wave, you don't necessarily have to go from crest to crest or from trough to trough. You can actually pick any equal distance part of the wave from one wave to the next if you're measuring in the exact same spot. For instance, if you measure right here, like where I'm pointing to, and you go to the next wave to right here, you can actually measure wavelength from here to here, which will also be the same distance from the trough to the trough. So it doesn't really matter. Now, a longitudinal wave is a little bit different. What you're really doing with a longitudinal wave is measuring either from compression wave to compression wave, or from rarefaction to rarefaction, or again, anywhere along equidistance between one wave to the next. So right here, you're indicating wavelength. So right here is the most compressed part of the wave, and right here is also the most compressed part of the wave, and as a result, that is wavelength. Typically, wavelengths are measured in distance, so that means you can measure in meters or kilometers, but typically the base unit in order to measure a wavelength is meters. The next wave characteristic is frequency. Frequency is really the number of wavelengths that pass a given point over a certain amount of time, and that is measured in hertz. So basically, this particular graphic on the right-hand side indicates a wave that has high frequency and one that has low frequency. So frequency is proportional, inversely proportional to its wavelength. So what that basically means is if the wavelength is actually shorter, like it is right here, each one of these waves, if it's passing, let's say, this point right here that I'm pointing to, each one you're going to have, in 1 second, you're going to have a lot more of those waves passing in a given second than the one down at the bottom. That's because right here, we're only seeing, honestly, 2 waves. And the wavelength here is, well, it's at least 1, 2, 3, 4, 5, 6, probably about 7 wavelengths less than the high frequency wave at the very top compared to the bottom. So that's why this is a low frequency, because in the same 1 second, we may only get 2 waves passing by compared to if this represents 1 second. Again, you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 waves per second versus 2 waves per second. So basically, frequency is proportional to the wavelength. So if you don't really know the wavelength, you can certainly get an idea the length of the wave by its frequency. Okay, so wave characteristics. Let's talk about the speed of waves. Basically, most of the things that we're talking about in terms of speed, let's think about light as well as sound, because those are the 2 very common forms of waves that we experience every single day. First of all, light typically travels slower the more dense material it goes through. So for instance, this graphic on the right-hand side right here indicates the speed of light. It travels in 1 second. So in a vacuum where there's no medium whatsoever, no matter at all, it travels about 186,000 miles per second. However, when we're talking about water, water is a more dense material, it travels about 140,000 miles per second. You take even a more dense material such as glass, now you're reducing it down to 124,000 miles per second, and you take a diamond, which we all know is very dense, very tough. Now we're talking about 77,500 miles per second. So as you go to a more dense material, the slower light travels. The opposite is true for sound, and that's because sound waves actually need some sort of substance to transmit that energy. So if each molecule in a substance is closer together, such as a solid, then the energy that's being transmitted is going to be faster. So we can see this is opposite in terms of, sound is opposite in terms of light. So if we look at medium right here, which is air at 0 degrees, we're traveling at 331 miles, meters per second. Air at 20 degrees Celsius is going to be at 343. We go to water, now we're increasing the speed. Lead, a little bit more dense material, we're increasing the speed again. Glass, and then eventually steel. So as you can see, as you go from gases, liquids to solids, the speed of sound increases. Finally, we're going to talk about wave behavior. So we talked all about the characteristics, now we're going to be talking about wave behavior. The first thing about wave behavior is reflection. So reflection is the bouncing of waves off an object, such as a mirror or other smooth surface. So what we're really looking at here is we're just looking at light. So you could see in this particular image of a mountain range, you could see the reflection of the mountains in the foreground in the water. So basically what ends up happening is what's on the right hand side. So basically the light that kind of comes in hits a very smooth surface. It will reflect, it will reflect in the equal and opposite direction. So right here would be called, where before the light actually hits the object, is called the angle of incidence. So this angle right here is equal to this angle over here, which is the angle of reflection. So basically, this is a fairly somewhat easy concept to really understand. So angle in equals angle out. And again, that's on a very, very smooth surface. Because if it's not a smooth surface, then sometimes you can get refraction. So what is refraction? Refraction is the bending of a wave caused by a change in speed as it goes from one medium, such as a gas, to another medium, which is called, such as water. So in this particular instance right here, we are looking at light again. You probably have seen something like this image with the pencil and a glass of water. And it looks like that it's bent. And the reason why it looks bent is because of refraction. Or even if you drop something in a pool, it doesn't always appear to be in the same spot as where you think it is before you start diving. Because as you look into a pool from the air above, looking through the water, you are going to get refraction, which is going to distort where the location of that object in the bottom of the pool is. Until you dive into the water, and then you're not going from one medium to the next, and you can clearly see where that object is at the bottom of the pool. So basically here what ends up happening is as you go from air to water, changing that difference in density really causes the angle in which that light travels to be refracted or bent. So I think a very easy term for the term refraction is really bending. Finally, we have diffraction. Diffraction really involves the change in direction of waves as they pass through an opening or around a barrier in their path. So right here, for instance, we have we have both passing through an opening in this particular image as well as a barrier in the path. So right here, as this particular wave goes through this opening between these two rocks, you can see clearly it's not quite as bent, but after it goes past, you can see that it bends more and more. However, even on this side right here where there is no opening, it just hits the object, you can see right here that the waves, the physical ocean waves, actually bend as well. And you can see in this particular area right here that they kind of cross over a little bit as well. So that's diffraction. So the big idea here is wave properties really include several characteristics about them, which includes amplitude, wavelength, frequency, and speed. And once waves get motion, they can be reflected, refracted, or diffracted. So now that we know the basics of waves, what I'd like you to do is please take the quiz to check for your understanding. Thank you very much, and have a great day.